talk about linearity, and we're going to see if a set of points, if a table is linear or not. And an important part to know here is, what is linearity? What does it mean to be linear? Well, linear relationship always has a constant rate of change. Well, now it's important to know, what is a constant rate of change? Let's look at an example table to see what constant rate of change means and how we apply it. So this is a table. We have our x's and our y's, and we're going to see how many are our x's going up by. Well, it's going up 2, up 6, up to 6, up 2, and up 2. Here on the y's, it's going up 1, up 1, up 1, and up 1. So because all the x's are going up by the same amount, plus 2, and all the y's are going up by the same amount, plus 1, this means that it's linear and it's going to have a constant rate of change. The way to find the constant rate of change is to see what's the change in the y's over the change in the x's. So the change in y's is how many we're increasing or decreasing by. So that's 1. The x's was 2. So that would be our constant rate of change. The way I like to abbreviate that is by saying the CROC. And no, I'm not talking about the popular shoe that everyone likes to wear. I'm talking about the constant rate of change. Rather than writing out every single time constant rate of change or saying it, I like to call it the CROC. So let's take a look at more tables and determine if they are linear or not. We have in this table x and y values. Our x's are going up by 1, by 1, by 1, by 1. So that checks out. All the x's are going up by the same amount. But let's look at the y's. We're going up by 3, by 3, by 3, and by 3. All the y's are going up by the same amount. So that means we can find a CROC. We can find our constant rate of change, which is the change in y's over our change in x's. So it's going to be linear because we have a CROC of 3 over 1. And we know 3 over 1 is just 3, so let's just write it as 3 for simplified version-wise. So this is going to be linear because we have a CROC of 3. This would still be linear if we got rid of this point. If we got rid of this point and we added by 6, added by 2, that simplifies to 6 over 2, which is 3. As long as all of them simplify to 3, we are good, it's linear, and we have a constant rate of change. Let's see another problem. So for this problem, we are going up by 2, up by 4, up by 2, and on this side, we're going down by 5, down by 10, down by 5. So let's see if our ratios are equal, and then we would have a constant rate of change. So I have negative 5 over 2. I have negative 10 over 4. Are they equal? If I simplify negative 10 divided by 4, that does give me negative 5 over 2. So it is linear, and it has a CROC of negative 5 halves. That would be my explanation as to why it is linear. Always have to explain how we got our answer. Let's see the next one. So for this problem, we are going down by 2, down by 2, and down by 2. On this side, we are going up by 4, up by 2, up by 3. So if we look, we have 4 divided by negative 2, 2 divided by negative 2, 3 divided by negative 2. And as the mathematicians that we are, we know those 3 rates are not equal. So these are not linear because we have no CROC, no constant rate of change there. All 3 ratios, or y's over our x's, are different, so it is not linear. So if I give you a set of ordered pair points, and we want to determine if it's linear or not, I suggest putting them into a table. And it's important which way we put them into the table. I would put it by smallest x value with its parent y and keep on going. So here's an example we can look at. if I have these 3 points, we can see our smallest x value is -1. That pairs with -2, so we're going to put that in the table first. The next part we have is 5, 4, and then the next highest one is 8, 7. Now we're going to determine this is linear or not by seeing if it has a CROC. So -1 to 5 is +6, 5 to 8 is +3. On this side we have another +6 and another +3. So 6 divided by 6, is that equal to 3 divided by 3? It is. They both simplify to 1, so it's linear because we have a CROC of 1. So like I just showed you, it's important to put these points into a table from smallest x value to biggest to determine the CROC. But let's try another problem just in case that was a little bit confusing. So now I give you the points 8, 1, -2, -5, 3, -1, and -7, -9. The smallest x value here is -7, and that goes with -9, so let's put that in first. Then we have -2, -5. Then we have 3, -1, and our biggest x value is 8, so let's put the 8, 1. So as you can see, smallest to biggest x values, they have their y's paired with them. So let's see if there is a constant rate of change. So this is going up by 5, up by 5, up by 5. So our x's are going out a pattern that we like. This is +4, +4, and +2. So now we see we have 4 divided by 5, 4 divided by 5, 2 divided by 5. 4 divided by 5 is not equal 2 divided by 5. So that would be not linear. We do not have a CROC. Why I showed you this problem is because some of us may be like, oh, the first two have a constant rate of change, I'm done. No, we have to look at that last one because that might not have a CROC with the rest. And as you can tell, it doesn't. So it does not have a constant rate of change. So it is not linear. So I'm hoping these example problems help you to determine if a set of points, if a table is linear or not, and how we would apply our rules for constant rate of change.